So two things to start with. There is a quiz tomorrow in section. Runs like everything else. We'll try to get the grades posted 7 o'clock or so Friday evening so that you'll have a chance to know exactly how much design project you need to do over the weekend and next week. We have today's lecture. We have another lecture on Tuesday, but that's it for the lectures. No lecture a week from today. And we also, tomorrow in section is the quiz, but after that there's no more recitation sections. So next week, aside from the one lecture I'll give I'll actually show you a working beta, so that'll be fun. But other than that, it's really finishing up all the checkoffs for labs 6, 7, and 8, and whatever you want to do on the design project to get whatever points you need. The second thing I wanted to ask was that MIT does these online course evaluations. I get a lot out of those, and so if you can take a moment to sort of go through and evaluate us, and in particular pick a box, it doesn't really matter which one you pick, to type in whatever comments you have about what went right and what went wrong. That's how the course improves. So the course you're seeing has benefited from the comments from previous semesters, and pay it forward. If you can just take a moment and let us know, that'll be very helpful. Thanks. Okay, so we're going to shift gears a little bit today. We've been spending some time thinking about how to make programs run faster. And the last couple lectures were all about pipelining the beta, where we're taking basically a single program. Here's a single program. And we're interested in running it as quickly as possible. And of course, in the end, it's not the assembly code that's important. What's actually important in the execution of the program is the list of instructions that gets executed in the course of running the program. So in the case of a loop, the actual back and forth, going back to the top of the loop and coming down again is sort of important to our ability to execute it very expeditiously. And in particular, the fact that we're going through this loop many times means, for instance, in caches, that once we get these instructions into the cache, they'll be there the next time we go look for them, and assuming the cache has the right architecture. So that means that these sort of repeated executions of particular instructions is one key for us to be able to execute programs much more quickly, because for example, our cache architectures actually work. So if I actually want to think about what it takes to execute this program, I'm sort of interested in the total path length, the total number of instructions that get executed. Okay, and we've been working hard on trying to execute each instruction as quickly as possible. So we introduced pipelining to sort of get the clock rate of the processor up. And so if you think of the total time it takes to run a program as the total number of instructions times the clocks per instruction, that's 1 for us. So if we take the total number of instructions and we're doing one instruction per one clock per instruction, and then we have how many clocks per second, and pipelining allowed us to get more and more clocks per second. That was the goal of doing our pipelining. And so today what we're going to try to do is to see if we can improve on the number of clocks per instruction. We'd like to make it, if we could, less than 1. Our machine does 1 clock for each instruction, 1 instruction per clock. That's either way, that way. But the question is, can we do more than 1 instruction in a clock cycle? Can we do 2 at a time? And so we'll spend a little bit of time thinking about different ways of gluing together our processor building blocks today to figure out if we can have the effect of getting more than 1 instruction per clock cycle. And you see that the machines that you have in front of you will actually be a collection of these techniques, a hybrid, and I'll point that out as we go along. So there's 2 opportunities here. One is instruction level parallelism. So that's you have a single program that you're trying to run, and what we're going to try to do is to execute more than 1 instruction at a time. And as we'll see in the next slide, sometimes that's pretty easy to do, and sometimes you're sort of saying, gosh, those, I can't do them both because I need the first one to finish before I can do the second one. And so it's sort of struggling with those sorts of constraints that make instruction level parallelism hard. And a lot of transistors inside your Intel chip are devoted to finding things that can happen in parallel, and then having a couple different functional units which can operate on two different instructions at the same time if the semantics of the program allows that. Maybe more realistically, and this is sort of the direction things are headed in, is thread-level parallelism. So that means we actually have two different independent things, and we're just going to execute them both at the same time. And the net effect is the machine is busily executing 2 instructions or 4 instructions at once, depends how many cores you have. Some of you have 2-core machines, some of you have 4-core machines. And the reason everybody's happy to run in parallel is there's no what's happening in program A has no effect on what's happening in program B. So in fact, you can execute one instruction from each program without worrying about, do I need to wait for the first instruction to finish before I can do the second? The answer is no, they're in different programs. So thread level parallelism is sort of, it's easy from a hardware point of view and maybe even easy from a software point of view. Okay, so if we take this big program here, and what I've done is I've rewritten the program to show you sort of the precedence constraints that need to be in place and for the execution to proceed correctly. So for example, this instruction loads a value into R1, which is then used by the next instruction. So we clearly can't execute those two in parallel because the compare has to wait until the load finishes. And you can see the first couple of instructions have to be done sequentially. Branches actually are a separate challenge because they represent a point which changes potentially the path of execution, which would mean that these instructions down here might be executed or they might not. It depends on whether that branch is taken. If that branch is taken, we won't execute these instructions. So there's some opportunities from parallel. We can look and say, oh, look at those instructions down there. I can run them in parallel. But depending on the branch, I may or may not want to run them at all. And we'll talk a little bit about how to solve that problem in a second. Down in the lower part of the program, you can actually see that it's possible to put a lot of instructions in parallel. Now notice that not all of these, so here's 2 of the loads, here's a 4th load. So I actually have to scan pretty far down the program, for example, to find these 3 instructions that can be run in parallel. The first 2 were right next to each other, okay? But if you keep going down, you discover this load is in fact doesn't depend on any of the earlier instructions here. So it in fact could be done in parallel with the first 2 loads. So in general, to get good instruction level parallelism, there's this notion of looking pretty far ahead of the program because you may actually have to go to sort of a new calculation entirely to find one that's independent of the earlier instructions. So it's sort of interesting to sort of look at this and you say, wow, but this is pretty good. Here we're executing 3 instructions in parallel, or 2, or 3. Here's another 3 down here. So these all represent opportunities where, in fact, instead of taking all of these cycles, we might be able to do this program in 6 cycles, assuming we could execute up to 3 instructions at a time. And that's noticeably shorter than the entire loop here. And as I say, Intel has put a lot of engineers on this job. One thing that's interesting to notice, though, I mean, we talk about the loop structure of programs as being sort of one of the key things that allows us to execute programs well. One of the neat things to notice, in fact, is that often iterations of a loop are, in fact, independent of one another. Often you're doing a bunch of things depending on the index, or if you're doing a bunch of operations in A sub I and B sub I and C sub I from 3 different arrays, and it's complicated, and there's not a lot of parallelism there for a particular I. When you go to the next I, all the operands now are completely independent of the first generation, or the first time through the loop. So in fact, this notion of loop unrolling often gives us an opportunity to find lots of parallelism that could happen if we're willing to think of how to do 2 iterations of the loop at a time. So imagine that I had written this out instead of changing the index by 1, I actually put 2 copies of the loop code and then change the index by 2, where the second copy uses the index plus 1. And I would discover that perhaps many more opportunities for instruction level parallelism. And in fact, things like the GNU C compiler spend some time doing these loop unrolling optimizations in the hopes of providing enough grist for your fancy processor to use the grist for the mill for it to be able to say, oh, look, I can my fancy 8-issue machine can suddenly has a lot more. I have a lot more different instructions that could potentially run in parallel because they're coming from different iterations of the loop. Okay. In general, it pays to, if you know that you're sort of playing this game, you can try to write your code in a way that unhooks unnecessary dependencies. But inevitably, there's going to be some dependencies. It's not like every calculation is independent of every other calculation in most programs. Typically, there's a set of things that you're doing where step 2 depends on the completion of step 1, and that gets in the way of instruction-level parallelism. What would a piece of hardware look like? So this is a diagram that's not unlike the block diagram for a modern Intel processor. You can see, in fact, instead of having one ALU, in most Intel processors actually have multiple copies of these blocks. So here's an integer ALU, here's a floating point ALU. The load and store operations are handled by a separate unit. The branch operations are handled by a separate unit. And then each of the units has its own little queue of instructions that have been given for it to do. And so the way it works is we have this big instruction queue. And at this level, the processor is saying, could these two operations go in parallel? For example, if N1 doesn't depend on the instruction here, if this second instruction, does that depend on this instruction or not? If not, they could be issued in parallel. And so this is a so-called dual issue. It can issue up to 2 instructions at a time. The most modern processors can look at 8 different instructions, particularly if they're going to 8 different functional units. They can say, I can do these all at once. And you can imagine it takes a lot of transistors and logic gates to figure out whether 8 different instructions are all independent of one another. It's sort of like bypassing in spades. You're looking, is anybody using this destination register? No, okay, then we can go off and run in parallel. So these get issued to the different processors, and then each one of these functional units here, I should have said functional units. Each one of these functional units takes its own sweet time. Integer functional unit may be in every cycle complete. The floating point may in fact take many cycles to complete. So eventually each of them, and the memory, access to the cache and the memory depends whether there's a miss in the cache. All of these different functional units produce results, perhaps not in the same order that the instructions were issued in. And so there's a reorder buffer that takes all the results and puts them all back into the correct order and then makes sure it makes the changes to the register files appropriately. And then each of these guys, whatever instruction is about ready to start executing in it, says, I need these operands. So there's a whole set of wires here on the operand buses that allow each functional unit to communicate to this giant register file that has umpteen read ports. Psst, give me register 2. I want register 5. And so there's an ability to ask for a lot of registers in parallel and actually get them all shipped to the different units, complete with the forwarding pass, the bypass pass. It knows what's waiting to be written in the register file and says, I haven't finished the writes yet, but here's the value you want. So the reorder buffer is keeping track of which registers are going to be written, and it waits until it gets so there's an add instruction. It knows it's going to write register 5, so there's an entry in here. Register 5 is going to be written by this instruction that's currently in functional unit 2, and so when the functional unit 2 finishes up, it can say, okay, I've got that answer, I can now go ahead and write it. Meanwhile, anybody who asks for register 2 can sort of be told, this functional unit is going to write it, but I can't give it to you yet. So all of the scoreboarding, keeping track of who's doing what and when gets pretty complicated, but if you spend enough transistors, there's the opportunity now to execute multiple instructions in parallel. Big, complicated beast. If you're interested in this sort of detail about modern processor architectures, a great course to take is 6.823. So that's a graduate level architecture course here. You'll be amazed at the extremes processor architects go to these days in order to deal with making your program work well. Now, remember before I talked about branches and the fact that something branches, you don't know whether you're going to execute certain instructions or not. Speculative execution is just saying, well, I'm just going to go ahead and execute them anyway. When I find out what the branch does, either I'll keep the results or I'll throw them away. And actually, a fair percentage of the work that your processors do is done speculatively. In other words, they're instructions that follow some branch, and the processor's just saying, well, you know, I'm ready to run 5 instructions at a time, so I'll do both where the instructions following the branch and the instructions of where the branch is going to. I'll just execute both of those instruction streams, and in fact maybe get a lot of potential parallelism because they're coming from different parts of the program, and I'll just save whichever results turn out once I know what the branch does. So I think it's sort of neat. I mean, this is a... But you can imagine all the details you have to keep track of, and getting it right can be somewhat complicated. Now, so that's one approach, is this sort of big, hairy processor that attempts to execute multiple instructions from a single program at the same time. A different approach is basically to make the evidence, you know, the existence of these multiple functional units just explicitly part of a program. So this is a SIMD, a single instruction multiple data. I have one instruction, and then I have multiple functional units. And maybe the easiest model to think of is vector arithmetic. So you might have an instruction over here that said vector add vector A plus vector B equals vector C. So think of these as like the add instruction for registers, except that each register, instead of being a single value, now is a whole vector of values. And when you think of writing a program that way, you can see that, in fact, if I have a different functional unit for each element of the vector, I can get a lot of parallelism. So I don't have to search for parallelism. Now the programmer is telling me explicitly by using vector arithmetic that you can do all these vector adds for each element at the same time. Those can be done in parallel. So these SIMD architectures are very attractive because the hardware is very straightforward. There isn't a lot of searching for something, you know, that can be done at the same time. We basically give you an instruction set where you can say, you know, I've got a 1,000 element vector. I want to add it to another 1,000 element vector. There you go. There's 1,000 adds that can all be done in parallel. And, you know, if you've got 4 functional units, you should be able to do it in 250 cycles. So this is sort of neat. In fact, it's so neat that there is a question about conditional execution, which is interesting to think about. So suppose you say, if, you know, element I is bigger than element J, put a 0 in, or if A sub I is bigger than B sub I, you know, write a 0 in C sub I. You say, oh, I can do all that in parallel. The trouble is that if you think about doing it in terms of a compare and a branch, there isn't one program I could write, right? Because, you know, some of these guys will say, I'm bigger, I'm going to branch, and other guys would say, no, I'm not bigger, so I'm not going to branch. So there's a sort of notion of, oh, well, how do you deal with sort of conditional execution? And the way the processors deal with it is they actually, instead of branching, you simply set a flag. If A is bigger than B, A sub I is bigger than B sub I, set the flag. So some processors will set the flag and other processors won't set the flag. And then you have these conditional execution things that say, do this if flag 1 is on. Now all the processors can do that in parallel. Some of them will have the flag on and some won't, so some will actually do it and some won't. But you only have one program that's able to do data-dependent execution in each of the separate functional units. And in fact, a lot of modern processors, because branches are so expensive, right? Branches, every time you do a branch, you have branch delay slots and annulments that have to happen, bubbles in the pipeline. It might be simpler, particularly for very short little chunks of code, you know, 1 or 2 assembly language statements and an if, to actually do this conditional execution. No branches involved, right? So there's no disruption of the instruction stream. So it might actually work better to do this sort of conditional execution hack. So they're starting to appear in most modern instruction sets, this notion of a conditional thing. Now you guys actually own a big SIMD unit in your Intel processors. They come with one of these built in. It's called the multimedia instruction set or SSE instruction set. And think of that as it's a big ALU and a big register file. This particular device only, you know, it only does register-to-register operations, right? So loads and stores. So there's the program that's running on the ordinary processor. So this is a separate coprocessor sitting off to the side. Is the ordinary processor is the one in charge of loading up these registers and storing them to memory. But once information is loaded into the registers, you get this special unit that's capable of doing arithmetic between these registers very quickly. And you sort of go, well, can an ordinary processor do that? And the answer is yes, but the neat thing about these SIMD units is they're able to do a 64-bit operation or two 32-bit operations in parallel. And you say, well, how does that work? Well, you just take the 64-bit ALU and you come along and you cut the carry line between the bottom half and the top half, and now you have two independent 32-bit ALUs. And you can keep doing that. You can turn it into four 16-bit ALUs. So a lot of the graphics acceleration you do, or multimedia encoding and decoding for watching movies, or encoding your voice in Skype calls, whatever. Now we're working on four different operands in parallel. So, four 16-bit operands. Same basic hardware, we're just fooling a little bit with the carry chains to reuse it to say, look, think of this as four 16-bit numbers. So a lot of the video encoding stuff is, working on, for example, these little 8x8 macro blocks. And there's operations, that's 64 pixels. There's a lot of operations that are happening in parallel on each of the pixels. So if you thought of that, think of this guy as dealing with 4 pixels at a time. Right, so now we're actually using one instruction, just a SIMD unit. One instruction is actually operating on 4 pixels. So instead of taking 64 operations, it'll only take 16 operations using this unit. And that's why these coprocessors are there, because a lot of sort of multimedia stuff these days that can take advantage of that. In fact, they go all the way down to 8 bits. So then the instruction set, look, do an add, but think of all the operands as 8 bits, or think of them as 16 bits, or think of them as 32 bits, or think of them as 64 bits. So you actually write these programs that, instruction by instruction, sort of tell the machine, should it think itself as one big 64-bit machine, or should it think of itself as 8-bit machines? It's a really neat idea, and it works very well. It's a godsend. I've been able to do a lot of real-time digital signal processing. So if I can write programs that run on these, just a standard laptop, that are able to, basically, tune in radio stations completely in software. I mean, it's capable of running quickly enough that I can do all the digital signal processing that you learned in like 602, the demodulation, down to baseband, the IQ extraction and things like that. I can actually run those in real time because of these SSE units. So this was a good idea. This was a good idea. Specialized instruction set is a special program. We write our routine specially to use this instruction set, but it's worth it for something that I'm going to be doing day in and day out. So SIMD was a great idea. It's not general purpose. These are accelerated for very specific sets of operations. Now here's a different idea. This notion of letting the programmer deal with it. This idea is popular, and then it goes away, then it comes back, and it goes away. So we're sort of in a going away part of the cycle. But the notion is I have all of these functional units. I have, a couple integer units. I have a floating point multiplier. I have a floating point adder. I have all these guys. What I'm going to do is, instead of building this hairy piece of hardware that takes a simple program and says, okay, you first functional unit, you do this add, and here's another add the second guy can do, so forth and so on. Instead of having the hardware figure that out, I'm just going to think of this as a giant instruction where I'm going to explicitly say, well, here's what the first integer unit does. And you can see that sort of looks like a beta instruction. Opcode, RC, RA, RB. Here's the opcode and the 3 registers for the second integer unit, and then the floating point operations, and the what I should be doing in memory, a load or a store. So I'm just going to let you, it's like a giant piano, and you can play whatever set of chords you want in order to keep all the functional units busy. And then we'll let the compiler worry about how to take a standard program and do a good job of filling up all of these very long instruction words. So it turns out that for some types of code this works really well, but mostly it's hard to take a program, a standard C program or something, and compile for this, because the C programmer hasn't made it clear which things can be done in parallel. it well enough for the compiler to say, ah, wow, I can really pack these in. Sometimes it works out well, but sometimes it doesn't. So, but VLIW is sort of a neat idea. What it does, it sort of, it's always good to, as an architect, to say, look, I have all these different things I can do. Maybe one alternative is simply to turn it into a programming problem. I'll let you specify what each thing should do. That would be a small matter of programming, SMOP. So that's always an architectural choice. It seemed attractive when this idea was first proposed by a bunch of guys down at Yale. They started a company, they were going to take the world by storm, and now you've never heard of them. So that sort of tells you what happens when bad things happen to good ideas. Or they turned out not to be, economically viable. This just wasn't enough of a win. So, okay. Now here's something that's got to be pretty obvious to everybody, right? If I have a beta processor, suppose I glue 5 of them together into one processor chip. I'm going to put caches as each of them so that mostly the betas, when they do memory accesses, are interacting with a cache. Occasionally there's a cache miss and we have to go off to a large shared main memory. And the notion is we'll be running a different process in each of the betas. And so that's what you've bought. You've bought a 2-core or a 4-core Intel processor. Their memory hierarchy is a little bit more complicated. They have several levels of caches, but this is essentially an abstraction of what they do. So this is called a symmetric multiprocessor. So it's MIMD in the sense that each beta is running its own instructions on its own data, so multiple instruction, multiple data. And to the extent that these guys have to communicate with each other, they can use semaphores, they can use shared memory buffers, they can, whatever you want. So, and we've talked a lot about how to program things. We have producer threads and consumer threads. Well, now they can all be running literally in parallel on different processors. So we're going to spend a little bit of time thinking about the implications of this architecture. Does it work? Does it not? Where are the problems? And we'll discover it'll be sort of like the problems we had when we did pipelining. It seemed like a really great idea. Stripes across the fish will just break things up. And then we discovered it sort of broke the execution model. We're going to discover the same thing here and similarly talk about neat fixes to make it work. Okay. So the first question is scalability, and the second is, how do these programs sort of keep track of what everybody else is doing so that they don't do something stupid? So scalability is sort of neat. I mean, they seem pretty scalable. It should be 5 things can run at the same time, but there's a bottleneck in this picture. What's the bottleneck? Yeah. Well, there are, to the extent that even though the caches are soaking up most of the accesses, there's getting a lot of cache hits, there's enough traffic on here that eventually becomes the bottleneck. Now, there was a Clinton campaign where James Carville had this great sort of rubric, it's the economy, stupid. Well, nowadays the rubric in processor designers is the memory, stupid, right? It's the memory that's the bottleneck. So if you go, you say, well, I'm going to keep scaling this. This works great with 4 cores. I'm going to put in 2,000 cores. And what you discover is at that point you can't build a memory system that can keep up with all the traffic. Even with good caches, the miss rates are still non-trivial. I mean, 1 or 2%. And when you have 1,000 cores, now all of a sudden this shared bus and shared memory is completely overwhelmed with requests. So there's a real limit to the scalability you can go with this sort of shared memory architecture. And I'll show you some slides toward the ends that we start trying to solve that problem separately. Okay, well, let's think a little bit. Does this even work? Let's see how this would work. So here's 2 processors. Process A is going to run on P1 here, and it does these 2 steps. It sets a value to a variable and prints the other variable. And the variables are living off here in shared memory. So 2 variables, x and y. Process A changes x, prints y. Process B changes y and prints x. Okay. And these guys have processors, caches attached to the processors, and we in fact can see that the caches are currently holding the values x equals 1 and y equals 2, which is sort of where things are starting before we do the execution here. Okay, so what are the possible outcomes? Let's actually watch this work. Well, process A sets the value of x to 3, it changes it in its cache, and then goes off and prints y, which it finds in its cache. It finds this 2, so it'll print 2. Process B changes the copy of the y in the cache to 4, says print x, oh that's okay, I'll go off and print the copy of x in my cache, which is 1. And in fact, independently of how I chose the order of execution here, assuming that all the memory accesses are hitting in the cache, and they would because we have both the x and y memory locations in the cache, we discover that these, whatever the order we go between these two processes and say you first, and then you run, and then I run, and so forth and so on, the program always prints 2 and 1. Right? A always prints 2, and B always prints 1. And that's great. It seems like, okay, looks like this model is working well. Okay. But just to double check, let's actually see what would happen if instead of running the two programs in parallel, we run them on a single processor and sort of timeshare one processor between them. And now, since we're running back and forth here, the sequence here matters. And we can see sometimes x is changed before it's printed, and sometimes it's changed after it's printed. And we look here, and for each order of execution now, we can see that different things get printed. And you're looking and say sometimes the programs print 2 and 3 if the order of execution is this. Here down here it's printing 4 and 1. So that's great. But what's you sort of say, well, okay. This seems to suggest that depending on the order of execution, the meaning of this program is different. But what's weird about this, if you look at these values and you look at the values on the previous slide, what do you notice? Well, what you notice is that 2, 1 didn't correspond to any interleaved execution on a single processor. So this, now we're sort of getting down to the real nub of the matter of what is the meaning, what's the semantics. If I give you a program that's meant to run in parallel, what do I expect the answer to mean? Well, one such answer is called, to the meaning, to the semantic question of what do these programs mean, what should I expect as legal answers, is that execution should correspond to some interleaved execution on a single processor. Right? And if I object to a particular order, I'm saying, well, this interleaved execution sometimes produces answers I don't want. I can use semaphores to make sure I rule out interleavings, to put in precedence constraints to rule out interleavings that I think of as incorrect. So we learned how to do that, 3 lectures ago. But if we look at this, we can see that the possible, from the previous slide, we can see here's possible sets of semantics. This would correspond to no valid interleaved execution. So our current processor model does not exhibit what we call sequential consistency. So it's an interesting question. When I first learned about this, I said, well, it does seem to me that we should have some standard for what two programs running in parallel mean, particularly if they're accessing shared memory. I should be able to say as a programmer what I expect this program to do. And one model is that if I use the sequential consistency model, at least I have all the tools I need now to add semaphores to rule out interleavings that I think of are inappropriate. Some interleavings may be fine, other ones I would say, that's not what I want my program to mean. Our naive model of execution, okay, which just had the processors running in parallel using their caches, does not achieve any sorts of, it doesn't do sequential consistency. Okay, so, and what we're discovering is that the caches turned out not to be invisible. We wanted them to be invisible, but they sort of got in the way. And here's the problem. Let's look carefully at what happened. So if I say, look, maybe the caches just need to not keep the information in the cache. If I change the value of x in my cache, I should also change it in memory. Right, so if the program starts off and starts running, okay, the program starts running, what we'll discover is that that process 1 changed the value of x to 3, even though that was reflected off into main memory here. When I changed it in the cache, I also changed it in main memory. The problem is that processes 2 cache didn't know that the value of x changed. So the problem is not, even if I do write through, if I go change main memory, the problem is this cache over here, piece 2 cache, that doesn't know that the value of x changed. So maybe we can fix that. Okay, so the way we're going to do that, I love these eyes. We develop these things called Snoopy caches. Right? So a Snoopy cache is a pretty sophisticated cache. It does everything a normal cache does, but it also watches the bus to see if there's any transactions involving memory locations that it happens to have a copy of. So in this case, when program 1 goes off and changes the value of x in the cache, and then we do a transaction to change that value off in memory, change this guy, this bus transaction is visible to this other cache. It can say, oh, I notice you're changing the value of a variable that I'm caching. I'll update my value in my cache. Okay, so these Snoopy caches were quite, everybody said, oh, this really does solve the problem. Now we actually are back into the sequential consistency game, right? There's none of these notions now that it depends which order we do things in, right? If we're printing x before or after it changes, that'll determine what we print out. But at least we have a situation where if the value of x changes, everybody in the whole system now agrees that the value of x has changed. There isn't a notion of you think it's 1 and I think it's 3. At some point here, when I change it to 3, this Snoopy cache arranged for everybody now to think that it's 3. Everybody sort of get the idea there? So we have this sort of notion that everybody agrees, at a particular instant in time, everybody agrees what the value of a variable is. In clock cycle 12, and thereafter, the value of x is now 3. So this notion of being able, when I do a transaction, to update the values, or perhaps the cache will say, I haven't looked at the value of x in a while. You're obviously starting to change it over there in process 1. Why don't I just get rid of it in my cache? So the Snoopy caches have a notion that they can either keep updating their value or they can just invalidate the value. Say, look, I'm forgetting all about x. I'm no longer interested in the value of x. Okay. So Snoopy caches are sort of neat. And in fact, we can do better about having to do a write-through cache. And I don't mean to belabor this table too much, but I'm going to spend a second here because it's sort of fun to think about a little. So suppose nobody has read anything. And the first time I read, for instance, the value of x, I want to manipulate the value of x, what I discover is that, look, I'm in this column, and it's invalid in my cache. I'm going to go to memory. So I, as the first person to read x, go to memory, read x. I now have it. And since this notion, I didn't hear from any of the other caches, they all reported that they didn't have a copy of x. So every time I fetch something, the other caches are reporting to me if they have a copy. I don't really care who has a copy. I just want to know if there's another copy out there. So the notion of not only missing in my cache, but the snoop miss means I missed in all the other caches. All the other caches says, I don't got it. Now I know I have exclusive use. Now whenever I change that variable, do I have to do anything in order for everybody to agree on what the value of the variable is? No, I'm the only one who's got a copy of it. So I can write it. I don't have to do write through. I don't have to do anything expensive. I can just pound away on it in my cache and no one cares. Now what happens when you read the value of x? So it missed in your cache, but I say, psst, by the way, I have a copy in my cache. So when I see your bus transaction to fetch the value of x, I probably will supply my updated value of x. Instead of the main memory, I say, I have the most recent value because I changed it. It went from exclusive to modified when I wrote it. Since I have a modified copy, I'll give you my copy, and we'll all mark it as being shared. So now the caches understand that for particular variables, more than one person is interested in the value. More than one other cache is interested in the value. And every time with a shared location, any time that value is now changed, okay, I have to tell you all. I have to say, psst, the new value is x. So we're implementing the strategy that I described on the previous slide, where everybody gets to see all the changes. We're just keeping track of, if there's no one else who's interested in the changes, I don't have to go to all the expense and power and time in order to let everybody know. I only have to let you know if we're actually discovering that we're sharing a variable. So this fancy MESI protocol, Modified Exclusive Shared and Invalid Protocol, was a pretty neat idea. It works well when you have a handful of processors, 2 processors or 4 processors. It doesn't work well with 1,000 processors. Okay, because there's just too much communication that happens there. Okay, but for a small number of processors, we actually were able to come back and get sequential consistency. Now we could have a notion, we could have a very clear semantics of what it meant to run a program in parallel on multiple processors, accessing shared memory locations. Okay. Suppose we gave up on sequential consistency. Right, so we said, so solution one, pound in our hardware so that we can keep sequential consistency as our model. You want to know what your program means? Think of every possible interleaved execution of these guys running on a single processor, these two different processes running on a single processor. And I guarantee you that if you run them concurrently on two processors, that whatever happens will be consistent with one of the interleavings. And you say, okay, so that was solution one, and we figured out how to make Snoopy caches do the right thing, so we actually got sequential consistency. Solution two is to say, you know what? Forget that. We're going to adopt a notion of the meaning such that when a particular processor writes a value, every time it reads that processor reads it after that write, it will see the updated value. So there's this notion of a sequence of operations that happens on a particular processor, but there's no guarantee about what other processors see. Right? So we're giving up on this notion of letting everybody agree on the value of a variable. We're just going to say, you're running independently. If you access X and I access X, there's no guarantees that changes that you make to X will be visible to anybody else who's looking at X. And then we introduce, so we say, okay, that's going to be our new model. And then we introduce this new instruction called a memory barrier. Right? And most modern processors have adopted, when we get beyond what a Snoopy cache can handle, now we go to weak consistency and memory barriers. And the way the memory barrier works is it's an instruction that basically goes to everybody and says, please update your memories. Everybody's going to update their memories. After the memory barrier, everybody agrees on the value for all the shared locations. Before the memory barrier, weak consistency, that you could disagree. After memory barrier, you agree. And then there's only certain places in the program where we all have to agree. And it's sort of, there's a wonderful course taught by Professor Shavit on multi-core programming that talks all about weak consistency and memory barriers and basically how modern concurrent programming works on these fancy processors that go beyond Snoopy caches. So it takes a little work to rethink about how your algorithm should work in the presence of weak consistency and memory barriers. But it turns out you can make fairly large multi-core machines with tens of cores work quite successfully with this programming model. You just have to change your algorithms a little bit. So, is that a question? Yes?
How do you choose which different values the right one in the memory barrier?
Well, what happens is that if so typically, if you're both randomly changing the same variable, you're sort of, you haven't clearly come up with a semantics you had in mind. If you change it and I change it and then we say update it, we have to be prepared to deal with each of our values becoming actually the final value. The real thing is if you're changing something that I later want to share, and we want to make sure that I see your changes, we would put a memory barrier between when you made the change and when I read it. Right? So it's just establishing a certain point in time that we're going to say, okay, you stop changing it and I'll start sharing it. And the advantage of that is that instead of every time you change it, we update everybody. You can make all the changes you want, and then we sort of decide when I'm going to start sharing it, and that's when you put the memory barrier in. So it doesn't solve the problem of two people randomly making changes to the same thing, but the memory barrier makes it very clear semantically when the information is now available for everybody to see. Right? So you get all the advantages of a cache where you can keep changing it, and then at some point you say, I'm done with my calculation, please share with everybody. So you insert a memory barrier instruction, and now everybody else who wants to see that value through we access that shared location will see your latest change. So it works out pretty well. And Professor Shavit's course, you actually write programs that deal with memory barriers, and you can solve a lot of you get a lot of concurrency in these programs. And his course, I think, runs on 12-core machines, so you're actually figuring out how to use 12 cores to solve these sort of big, huge, traveling salesman problems and things like that, using this sort of semantics. So it's cute. So where are we going modern-wise? I keep with this whole notion of a shared memory. We struggled a little bit with either the Snoopy caches to deal with it, but we knew there was a bottleneck. Here's what a modern multi-core looks like. This is a 64-core machine. You can go out and buy them. There's a company called Tylera that was actually founded by one of the MIT profs here. And you can sort of notice that there isn't really a shared bus here. These guys basically just talk to their neighbors. You can send messages to the edge here. Please, and there's a whole bunch of, memory arrays that hook off to the edge here. But if this processor wants a memory value, it sort of has to communicate with the edge and says, get me this information from memory. Typically a whole block of words, which can then be routed back and put in that processor's cache. So think of this as not so much as processors with some communication. This is processors with communication. So this chip is really all about the communication message, communication channels. And in fact, it's really the communication things that where all the architecture went, all the architectural design went, and figuring out how to do all this sort of message-based communication with the peripherals and then with each other in the different cores. So you have to rewrite your programs. The advantage is that by and large you're getting away from sort of shared memory as doing semantics, and you're replacing that with explicit message passing, which these machines can do very, very well. So, for example, one of these 64 machines can actually do H.264 encoding for like 100 TV channels at a time, 100 independent TV channels at a time, right? And you say, well, if I had to take my one processor and write a program to do that, it'd be very complicated. I'd have to figure out, when it's like keeping 12 plates all spinning at the same time. Some plate over there would need attention. I'd have to go back and make sure I did a little bit more on channel 1 before the people viewing channel 1 ran out of bits to see. Here, you can sort of say, well, each one of these guys is working on a separate channel. And by and large, so long there's enough memory bandwidth, that can be made to work. Okay, so these big MIMD arrays are really what people are starting to buy. Intel had a project called Laramie, which they were trying to sell you an 80-core version of something like this. So people are, there's other than Tylera, I don't think there's people who are out there yet. Some of the big Cray machines, the big multiprocessor Cray machines, the Titan, for example, is 500,000 AMD cores all lashed together with these big communication channels. So, there's in supercomputers now. They'll probably be in your laptop in a couple years. It's part of the way we're going. Yes, sir?
I'm assuming the 700 megahertz and 2.3 gigahertz are what is the clock speed?
Yes.
What makes it be so low compared to?
Do you see that number? That's the power dissipation, 250 watts, right? That means that if this thing is not basically water cooled, it melts, literally melts. It'll unsolder itself from the board, right? So these things get very, very hot. So the real limitation nowadays is just, we can only dissipate so much heat off of these chips, even with fancy cooling systems. And so these clock rates are almost all determined by how much power dissipation your cooling system will provide. All your Intel chips, they have different, they're forever adjusting their clock. They sit there and there's hardware that looks at the temperature of the chip and reduces the clock rate if the temperature gets too high. So they're actually, your 4-core chip, if you're running on all 4 cores, the clock rate is, half or 2/3 of what it is. If you're running on 1 core, they have this turbo boost. So they're willing to let 1 core run really fast if the other cores aren't doing anything, because you can use up some of the power dissipation that running fast is, because no one else is using that power dissipation. You can say, oh, I can run really fast, I'm going to get hot, but everybody else is cool. So the total power dissipation isn't outside the envelope. So anyway, so the power dissipation is what really has driven us to multiple cores. Trying to make 1 core run faster and faster and faster just turned out to be a losing game from a power point of view. Alrighty, so we've been talking a little bit about how to glue multiple processors together. We did pipelining, and that got us a faster clock rate, but at some point we run into the power dissipation problem and we stop. So we're not pipelining. You're not gonna see machines with more pipelining in them. We're sort of maxed out on the clock rate of of a single core these days. Superscalar, well, it's at its practical limits. We've sort of taking a standard program, we can issue up to about 8 instructions. After going to a 16-issue machine simply would not provide you with any faster execution, even though it would take a lot more transistors. SIMD actually works really well, H.264 encoding and decoding. So for particular applications, we build SIMD processors in to every processor chip these days because they work so well in interesting application areas. VLIW, everything goes back to software, but it's inflexible, and people have been able to make it work very well. Okay, there are some interesting models out there. Your brain has a very slow clock rate. The rate at which your synapses fire is pretty slow. On the other hand, it seems to do a lot of processing, right? And so there's clearly some secrets to massively parallel architectures that we all carry around with us, or at least examples of it, even though we don't really understand quite how it works. So there's obviously some room for improvement. How do we take a low clock rate, piece of wetware, but we're able to do all this very complicated audio-visual processing, pattern recognition. We're doing all these marvelous things with really pretty shitty computation, and we're interested in figuring out what the hardware analog of that is. So there's a lot of things that remain to be done about thinking about how to build large parallel machines, and that's really your job. My generation spent a lot of time taking a traditional single-threaded, simple RISC machine and making it faster and faster and faster. We've sort of gotten to the limits of that, other than making these big multi-core things. Okay, and we need some new ideas about how parallelism should really work, like in your brain, to see what the next generation of processing is. So I look forward to a 6004 student driving up in their long stretch limo and stepping out and said, those processors you're using? I invented those. And you can take me to lunch. I'll be glad to go with you. So good. I'll stop there. Good luck on the quiz tomorrow, and one more lecture on Tuesday next week, and then you're done.